Hello guys, welcome back to TechDose, and in this video we will look at smallest subarrays with maximum bitwise OR problem, which is from Leetcode number 2411. Let's now see the problem statement. You are given a zero indexed array nums of length n consisting of non-negative integers for each index I from 0 to n minus 1. You must determine the size of the minimum sized non-empty subarray of nums starting at I inclusive of I that has the maximum possible bitwise OR. In other words, let Bij be the bitwise OR of the subarray nums I to j. You need to find the smallest subarray starting at I such that the bitwise OR of this subarray is equals to the maximum of Bik, where I is less than equals to k and k is less than equals to n minus 1. The bitwise OR of an array is the bitwise OR of all the numbers in it. Return an integer array answer of size n, where answer at I is the length of the minimum sized subarray starting at I with maximum bitwise OR. A subarray is a contiguous non-empty sequence of elements within an array. Now, if you look at the example, let's look at the first example. In this case, if you take 1, like let's take the first element, what will be the maximum bitwise OR that you can get if you start ORing from left to right? This is index 0, index 1, 2, 3, 4. So if you start ORing this one, like let's OR this 1 with 0. If you OR 1 with 0, it will remain to be 1. Now take this result and OR it with the next item, which is 2. So 1 bitwise ORed with 2, it will be equals to 3. Okay. So you have got 3 at index 2. Now if you continue further, then 3 ORed with 1 will still be 3. And again 3 ORed with 3 will still be 3. So we got the maximum value for the first time at index 2 when I started from index 0. So what is the size of the subarray? Size of the subarray is 3, 0, 1, 2. Okay, so if you take the slice 0, 1, 2, the 3 element slice, and if you OR it, then you will get the maximum OR value for the 0th index, and the size of the subarray is 3, and therefore the answer is 3 in this case, right? If you repeat the process for this index 1 item, then you will have to take these 3 items 0, 2, 1, and the maximum OR value will be 3, but the size of the subarray is also 3, and that is why the answer is 3 here. Okay, if you take the last item here, I mean the second last item, so the second last item, if you take 1 OR with 3, you get the maximum value as 3. And you can't take any more item because you don't have anything to the right hand side. So the size of this subarray is 2, and that is why you have written 2, right? So that is how the answer is built. The answer is built by checking for each item, moving from left to right. When did you find the maximum OR value? What is the first index that you see the maximum OR value, right? So you saw that for the first item, when we traverse 3 items till this 2, then we find the maximum OR for the first time. You should also notice that when you find OR values, the value can only increase or can remain the same. It cannot decrease. Okay. So it is a non-decreasing type of value that you are going to get. So the first time that you get the peak item and you don't see any higher value after that, then this first time when it occurred will be the nearest index for any particular index that you are trying to find. Okay. So that is how the explanation is made here. I hope this entire problem is clear. So if you follow this process, that you look at the index and you iterate from left to right and see when did you find the maximum OR for the first time, then you might have to iterate for n times for first index, n minus 1 times for the second index, n minus 2 times for the third index, and so on, 1 time for the last index. So the total number of operations will be, you add it up, and that will be order of n square. Now if you look at the n value, it is 10 to the power of 5, and if you write an n square algorithm in this case, then that is going to be 10 to the power 10 operations, which will give you TLE for sure, because you know 10 to the power 8 is the standard for our 1 second. So we need to do something better than 10 to the power 8 computations. So looking at the constraint, you can make out that order of n is what I want, or maybe n log n, but I should not get a complexity more than n log n, right? All the values are less than equals to 10 to the power of 9. So you can say that it fits inside 32-bit integer. So I hope all the constraints are clear. Let's now look at some observation. When you want to maximize any number, then it will be equivalent to asking that set all the bits So whichever bits are already set, don't touch them, and whichever bits are unset, you make them 1 again. So then you will get the maximum value using a certain number of bits. In this case, if I consider 4 bits, then I can get the maximum value in 4 bits when all the bits are set. Okay, I cannot increase the value after this. So we need to just consider the unset bit and make them set. So maximizing a number using OR is equals to setting the unset 0 bits, right? Now let's take an example. Let's say that we are given the array 2 3 1 4 5. So I have written the weights. The weights is in the bottom up order increasing, and you can imagine that this 2 value is going to be 0 1 0. Now why I am writing in 3 bits? Why not in 4 bits, 5 bits, or any other set of bits? Because the number of bits represented here will depend on the maximum number. So the maximum number is 5 in this entire array, and the number of bits in 5 is 3 significant bits, and that is why I will be taking 3-bit representation for all of these numbers. Okay, taking any more bits will not make sense because those zeros will never become 1. Okay, the maximum number will actually define the significant bits, and that is why I will take the max number and find the number of bits, significant bits. So you can easily apply 1 plus log of maximum element. So that's how I got this 3 value, right? So if I represent all these numbers in 3-bit representation, then 2 will be 0 1 0. In this case, this second bit is already set. The first and the last bit needs to be set. We may be able to set it or not be able to set it. It depends. So what we have to do is we have to iterate from this 0 and try to set this 0th bit. That means the weight 1. The weight 1 is 2 to the power 0. This is 2 to the power 1 and this is 2 to the power 2. So this is the first bit moving from right to left. So this first is shown on the downside. So when I want to set this bit, I can set it at index 1. Okay, so the size of the subarray here is 2. And when I want to set this, then I will be able to set it at index 3. So the size of the subarray is 4. And this middle bit need not be set because it is already set, isn't it? So out of all this, what should be the minimum size of the subarray that I take so that I get the maximum OR value? The minimum size must be containing 0 to 3, because if I take any smaller size, then this weight 4 will not be set. So I will not get the maximum number, right? But can I take a larger size? Yes, you can go for 0 to 4 as well, and you will get the same maximum number as 111, which will be 7. But the smallest size is from 0 to 3, and that will be defined by whichever set bit is present at the farthest position to the right hand side. Okay, so you saw a bunch of zeros, and then you saw set bit for this weight 4 at index 3, and that was the largest distance, and that is why you have to maximize the distance over all of them, and so 4 will be the result, and that is why 4 is added for the distance value, which means that the smallest size of subarray starting at 0 to get the maximum OR value will be equals to subarray size 4. Now if you repeat the same for this index 1, then this index 1 is having value 3, so this is 1 1 0. For this first and second bit, you do not need to iterate anywhere, but for this last bit, if you iterate, you will find the first set bit at position 4. So what is the size of the subarray? 3. And that is why we will be writing 3 here, and the max value is all set bits, right? If you again do it for this index 2, then this bit need not be set, but this one you keep iterating and you will never find any set bit. So if you never find any set bit, then this value cannot be set, and so don't consider it in your calculation. Okay, because this cannot be set, so you do not add any distance value for it. You ignore this entirely. Now the third bit, can this be set? Yes, so this can be set at index 3. So what is the maximum size? Only this can be set and no other bit requires to be set, and so you can say that the distance value is 2 because the subarray size is 2, and that is why you got 2, and the max value that you can get is 101. So if a 0 bit cannot be set, then we will not be considering it, and if you already have a set bit, then we will not be considering that as well. If you consider this index 3, then for this 0, can you set it? Yes, I can set it at index 4. So the distance value, or you can say subarray size, is 2. Can you set this bit? No. So I will not consider this. This bit is already set. So there is only one value. Okay, and that is why the answer is 2. For the last one, the answer will always be 1 because there is no item to the right hand side. So whatever is the value, that will be the max value. Okay. Now this is the brute force approach, and you can imagine that if you have to iterate for any item to all the items on the right hand side, then you will end up getting n square. And so this technique will give you TLE. We already know that, right? But if you have already solved the next greater element problem, then you will understand that whenever you want to get information from the right hand side, then it is always advisable that you parse from right to left. Don't parse from left to right. Because if you parse from right to left, then you can maintain when did you see the set bit for the last time. And if you can maintain when did you see the set bit the last time for any given position, then you have solved the problem. Okay, then you can easily solve the problem. Like if I move from right to left, and let's say moving at index 2, when I reach to index 2, I will say that the set bit that I saw for this 4, that means the second position, the last set bit was seen at index 3. For this, the last set bit was seen at index 5. Index 5, why? Because this is out of bound. So when I say 5, this means that there was no set bit. The last set bit for this first position was seen at position 4, index 4. So out of all this, you can make out that if I want to set this bit, then the nearest set bit to the right hand side is at index 3, and currently I am at index 2. So what will be the subarray size? It will be 3 minus 2 plus 1, which is 2. Similarly for this 0, if I want to set it, nearest set bit is at 5, which is outside of the array range. So I cannot set this, so don't consider it. And the nearest set bit for this, I mean this is already set, so I don't need to set it again, right? So I can say that the subarray slice starting from this index 2 will be only of size 2, and that is how 2 has come, right? So in this kind of problems where you have to look up on the right side, try to traverse from right to left. If you had to look up from left side, then you will be traversing left to right, just like in the previous greater element. Okay, in previous greater element you traverse from left to right, in next greater element you traverse from right to left. So that same logic can be applied here. So let me show you a dry run on the same example. Now I will be traversing from right to left, and I will be taking a nearest set bit array. The array size will depend on the number of set bits, which I will be using the log function to find 1 plus log of the given number to find the number of set bits. Given number means maximum element. So max element is 5, and so the number of significant bits are only 3, and that is why I have taken 3-bit representation. So the nearest set bit will be containing an array of size number of significant bits, and each of the positions set bit will be contained, like when did you see the set bit on the right hand side. So initially I will be saying index 5 because index 5 is out of bound, so I have not seen any set bit. The distance will be calculated with the nearest position to the right hand side where you saw the set bit minus the current index plus 1 to find the subarray size. Okay, now let's start the algorithm. So when you start from this position, that means at position 4, then the nearest will always be assuming index 4. Okay, and I will try to go bit by bit. So this bit is already set. How do you know if a bit is set or not set? You can take the given number, whatever is the number, like let's say array at I, and if you want to check if jth bit is set or not set, you can just left shifted by j times, and you can check if it is set or not set, right, using an if statement. So this is how I will be checking it. If this is already set, then I don't do anything. If it is not set, like let's say it is 0 here, then I will be checking for this position 1, when is the set bit on the right hand side. So it is at position 5, which is equals to n. The n value here is 5, which is the number of item. If it is n, then that means I cannot set this bit, so just ignore it. And this bit is already set, so I don't need to set it. So what is the nearest index to the right hand side? It is still 4. Okay, so what will be the subarray size? Nearest minus the current index plus 1, which is going to be 1, and that is why the subarray slice size will be 1 here, saying that if you take a 1 slice subarray, then you will get the maximum OR value, and that is correct. So while calculating the set bits, whenever you say that okay, I have a set bit here, then you need to update the position. That means you saw a set bit now at the nearer position, right? So you will be setting it up with index 4. You also saw a set bit for position 2 at index 4, so update it. Okay, and now you move to the left hand side. Again you parse bottom up. You see that there is an unset bit, but can we set it? You check the value here. Yes, I can set it. This 4 is less than the n value, so I can set it. So the nearest value, which was assuming the initial value 3, will now be updated to 4. I will try to maximize the n value. Okay, now I will check this one. Can I set it? So the index is 5, which is equals to n, so I cannot set this, so ignore it. This is already set, so I won't do anything. Ignore this as well. Now whenever you find a set bit, I will be updating the index because I want to track the nearest set bit to the right. Okay, now whatever is the nearest position, take it. 4 minus the current position 3 plus 1, so the sub array size will be 2. That means if you take a 2 slice sub array from 3, that means 3 comma 4, then you get the maximum OR value. Done. Move to the next item, index 2, parse bottom up. You see that this is a set bit, so if you see a set bit, you don't do anything, but you update the index at which you saw the set bit, right? For this 0 bit, you see, can I set it? So this is saying index 5 on the right hand side, you have a set bit. So index 5 is actually out of bounds, so you cannot set it. Ignore it. This 0, when do we set it? At 3. So the nearest index that was assigned to 2 now will be assigned to 3 because 3 is larger than 2. And once we are done, then the sub array slice will be n minus I plus 1, which will be 3 minus the current index is 2 plus 1, which is 2 size. That means if you take a 2 size slice here, then I will be taking the maximum OR value. So the answer here will be 2 again. Move to the left hand side. Once you are at index 1, again move bottom up. When you see a set bit, I mean initially you will be taking the nearest index to be equals to the current index, which is 1. When you see a set bit, just update the index to 1 and don't do anything. Set bit, update the index to 1 and don't do anything. Unset bit, so when can we set it? At index 3. So 3 is larger, so update it to 3 and you are done. Once you are done, find out the subarray slice size, which is n minus I, which is the current index, plus 1, which is going to be 3. So if you take a 3 size slice from 1, which is 1 to 3, then you will get the maximum OR value, and so the answer here will be 3. And move to the left hand side. For this 0, move bottom up. When you look at this 0, see when you can set that bit at index 1. So initially the nearest index will be assigned to the current index, and you can set this first bit at 1, so update this to 1. When you can set this bit, actually this bit is already set, so it does not require to be set, but store the index. When can you set this bit? At index 3. Now 3 is larger than 1, so update this to 3. Okay, and you are done. Once you are done, find out the slice size, the subarray slice n minus current index plus 1, which is going to be 4. So if you take a 4 size slice from 0, that means 0 to 3, then you will get the maximum OR value, and so the answer here is 4. So you have built the answer array 4, 3, 2, 2, 1. Okay. Now in this case, you have just iterated through all the items moving from right to left. So that will be order of n in terms of complexity, but for each number you are parsing for all the bits. Okay, all the bits. So the number of bits can be 32 because you know that the number, that means array at I, mentioned in the constraint is less than equals to 10 to the power of 9. So maximum it will be a 32-bit integer, isn't it? So I will say order of n as the time complexity, but on runtime I will say n log n, because if you take the log of 10 to the power 9 base 2, then it will be around 32. Okay, it will be less than 32, around 32. So that is why the runtime will be n log n, but the amortized time will be order of n. In terms of space complexity, if you don't consider the answer to be extra space, if you just consider the algorithm, then you are taking the nearest set bit tracker, which is of size number of set bits, which is order of 32. So you can consider this as order of 1 as the space complexity. However, in runtime you can consider it as log n. Okay, so if n is your number, but here n and the item are two different numbers. N is actually less than equals to 10 to the power of 5, isn't it? N is 10 to the power of 5 maximum. This is the count of elements, but each element can be 10 to the power of 9. So if you consider each element value to be, let's say, b, then the complexity will be n log b. Okay, and this will be log b. So in amortized time, you see order of n and order of 1. So that's how we can say that the time complexity will be order of n, space complexity will be order of 1. I hope it is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the nums array and then finding the number of elements, the max value, and calculating the significant bits using the max value by using 1 plus log base 2 of max value. Now this problem is very similar to finding the next greater element, and that is why I have mentioned that we will be tracking the next greater item. We will be tracking the nearest set bit as I had said. So take the number of bits and then assign it to the n value. The n value will say out of bound. Okay. The answer array will be of size n and all of them will be containing initial value of 0. Right. The n will be different from the bits. The n will be the number of items in the nums array. Now you will be iterating for each of the item from right to left, and then for every item we will be taking the nearest to be the index I and try to maximize the nearest. So whenever I check bits and if the bit is set, then I will update the nearest set bit at j with I as I explained. Otherwise, if the nearest set bit is not equals to n, that means it is within the bound, and so setting a 0 bit will be possible. And if it is possible, then take its index and track the maximum nearest index, and that will be defining the minimum subarray size that you should take in order to maximize the OR value, and that will be stored in answer at I. So we need to repeat it for all the elements and return the answer array. So I hope this entire approach is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.